3 years ago, I gave here a talk about transformers. It was already a huge zoo of different transformers back then, tens, maybe even hundreds of different models. And I used this picture. Right now, transformers are replaced by different creatures like snakes, hippos, and others. You'll learn why is it so later. And this talk about what are other architectures available. From the first sight, you may feel that transformers are everywhere, and it's true. Almost every LLM is transformer. Vision right now dominated by transformers with vision transformers, and it's hard to say which places are still use other models, but there are a lot of life everywhere, and my goal is to highlight what's there. And I'll try to show you the variety and richness of this world. My goal is not to tell you and explain every possible architecture. That's just impossible. It will require several days. And my slides are heavily, how to say it, well, there will be a lot of links and texts, and the goal is to make these slides available to you in the offline mode, so you can follow them later and follow all the links and read everything you're interested in. So feel free to download slides. I'll publish them in LinkedIn, and organizers will publish them as well. So use them as a material to follow what is interesting to you. So let's start. Let's start with a recap how we came here. The common knowledge just 5 years ago was that there are 3 basic architectures, just feed-forward neural networks, or MLPs, multi-layer perceptrons, convolutional neural networks, CNNs, and RNNs, recurrent neural networks. And feed-forward neural networks are good for, say, general classification. Convolutional neural network, because of their implicit biases, were very good for learning image representations, local features, and some things like that. And recurrent neural networks, be it RNN, LSTM, GRU, was good for sequence processing. And that's the common knowledge, a typical recipe, what to start with if you face one of these problems. But in reality, life is not so simple, because there are good sequence model like machine translation that were convolutional neural networks. For example, Meta's team with Jan LeCun published several interesting works like that, but overall it's more or less true. Situation changed in 2017. Every one of you knows this paper, Transformer emerged. And what's important with Transformer is Transformer started using a new block called multi-head self-attention. It was much better in terms of computational efficiency. It was easily paralleled, and suddenly people were able to train really large models, and that gave rise to all these LLMs we have right now. And at the heart of Transformer lies this multi-head self-attention, and in the heart of it lies scaled dot product attention. And what's important in it is just you have what is called queues and keys, and you calculate dot product between them. So this way you find items. When you process a specific token, you find other tokens that are more or less related to it. And then with the weights found by using softmax after this dot attention, you calculate a weighted combination of other embeddeds, other tokens, and this way you process the whole sequence. And the important thing with attention is that it has quadratic complexity, and that's a problem because it prevents you in scaling, it prevents you in using really large inputs, and a lot of different works later was used to overcome this transformer limitation, to use linear attention, to use sparse attention, any other attention, and I'm not sure, hundreds or many tens of different models emerged. There are a lot of different models. And in a typical transformer, you can change almost anything. It's like Lego. There are a lot of moving parts. You can trick almost any of them. So no sense to explain everything in this list. It's just for visual representation that It's a big Lego. And one of the important directions was efficient transformers, to have linear transformers that is fast enough. And I took this picture from a well-known paper. And you see here sparse transformers, mixture of experts, which is popular right now. You see here some low-rank kernels, linear transformer, long form, and others, and a lot other things. Recurrence was added to transformers, and there are tons of different models. But that is not focus of our talk. I just highlight two architectures, kind of transformer-like RedNet. Retentive network was published by Microsoft. They are kind of reinvented original transformer block. It was changed a bit, added recurrence, and the model became better in terms of scaling, in terms of latency. That was interesting. Another interesting architecture was decoder-decoder, or Yoko model. It is much more memory efficient, and again, which is very helpful for hosting models. But again, that's not the goal of our talk. Yeah, and CNNs actually intersected with transformer field, and there are a lot of hybrids there. So it's a live field. There are many things happening there right now, but let's keep it as it is and switch gears and look what else are there. So what non-transformer architectures are here in 2024? Let's start with MLPs. MLPs, the maybe oldest neural network architecture, it is resurrecting right now, and several interesting papers were published. First of all, MLP mixer. It was interesting paper. Back then, visual transformer was used for, was started to use for image classification and other tasks, and it was good. And people asked the question, is it possible to have the same quality like visual transformer, VIT, but with old school architecture like MLP, for example? And they invented architecture called MLP mixer. It works on patches of images like visual transformer. You split images in, say, squares, 16 by 16 pixels, and pass it as tokens to the input, and special blocks like mixer layer mix these tokens first channel-wise, then patch-wise. And this way you both account for inter-token interaction and inside token interaction. And finally they found that the quality was really good, and you don't need a transformer to obtain the best possible quality. You can achieve it with almost vanilla, not really vanilla, but with pretty old architecture. And then a lot of other papers emerged. GMLP, almost the same as MLP mixer, emerged maybe in a week later, proposes similar thing. Another work just several months later describes all the variety of different MLPs that are using for image processing and other tasks. And you see the field is very diverse. And later people scaled just ordinary MLP without any mixer, and they found that it's competitive to transformers. You just need more data. Data augmentation is critical, and with slight minor modifications in architecture, you obtain good results. And what's interesting with ordinary MLPs, you have much better latency, say orders of magnitude better than transformer, and you have throughput even 2 orders of magnitude better. So, and in terms of computational efficiency, it consumes 3 orders of magnitude less computation. That's really cool for many production cases. That could be a game changer. So interesting work. Okay, that's MLP. Then CNNs. You may have a feeling that CNNs ended with, I don't know, ResNets and something like that, and then VIT emerged and now it dominates, but that's not true. One of the interesting papers was ConvNext. They reimagined good old ResNets and found that they can train really good models compatible to visual transformers, and even to advanced visual transformers like Swing transformer. I think the first version of it back then. Then suddenly people who trained EfficientNet, that pretty old architecture optimized for computer vision, showed that they're not worse than new ConvNext, and it's a great model. You can use it for image classification and no need for any transformer here. Then the same authors proposed a hybrid model, CoAtNet. It's a mix of convolution and attention, and again, it, in some sense, even better than EfficientNet v2. And just a recent update of this year, MobileNet v4, it's a hybrid model that incorporates something from transformer, some attention modules. Again, it's a pretty good model, and it's stated as Pareto optimal for on-device inference. Again, that's great. Right now, you don't have to use the single architecture that is transformer. You have a whole deal of very different models with good implicit biases, and which is fast, so it's great. And some other works like continuous kernel convolution or structural global convolution is pretty new work, sometimes from the authors of state space models. I will talk about them later. So it's a very live field right now, and a lot of things is happening there. The most fruitful part is RNNs, recurrent neural networks. It was already a very, very diverse field even before transformers came. Most people think that there are RNN, LSTM, maybe GRU, but that's very far from the whole picture. Even before 2017, when transformers came, there were stunning variety of, I don't know, very, very different transformers. For example, I'd highlight, you probably heard about neural Turing machines and differentiable neural computer by DeepMind. That was memory augmented architecture that used RNN plus some memory to solve potentially Turing complete tasks. And there were interesting models like neural GPU, for example, by Ilya Sutskever, by the way, and other interesting models like Grid LSTM by Alex Graves or AWD LSTM, which was really good. But that was just start, and even after transformer models started to dominate this field, new models still emerging. Mogrify LSTM was kind of top one model for some specific data sets for a very long time. It's very special kind of LSTM. And some other interesting models emerged. You definitely heard about RWKV. It's a recent model. I will talk a bit later about it. Very recent updates by DeepMind, LRU, Griffin. Interesting models. XLSTM emerged this year. So a lot of things happening here. RWKV was stated as a good alternative for transformer. It originally was trained on pretty big data sets, and you see almost any model proposes some kind of blocks that looks similar to what you see in the original transformer architecture, but some specific things are changed. But overall architecture is similar. You have stack of blocks. Inside this stack you see something for here for time mixing, then something for channel mixing. Usually it's some special block that includes, I don't know, convolution, special version of attention, some recurrence, and upper block is usually MLP or something like that. It's very typical, and a lot of architecture use this high-level approach. And what's interesting, I took this table from the paper of RWKV. It highlights the main parts where specific models are poor. For example, LSTMs, the typical recurrent neural networks, are very poor in parallel training because by design they are sequential models and you just can't parallel them. You have to wait until the previous states are calculated, and that's it. It's hard to parallelize these models. That was the main bottleneck with RNNs. If this thing was solved several years ago, maybe we don't have transformer models. We were happy with RNNs, but that's not the case. Transformer is bad in complexity of self-attention. It's quadratic originally, so that's a problem with training large models. Transformer is also bad in terms of time and memory for inference. Recurrent models maintain internal state, and to process additional token, you just use constant time. But for transformer, without any special tricks like key caching and some other things, it's ON. And some new models like RWKV, Mamba, and others look pretty good. It's constant time complexity in inference, it's linear complexity in training, it's parallelizable, and this set of features is the important set that almost any new architecture wants to target. Linear recurrent unit by DeepMind was a reimagining of good old RNNs, even not LSTMs. The idea was let's add some specific things like very special form of matrices inside. Let's remove nonlinearities, and suddenly these models become parallelizable, and the original goal was to match performance of state space model. Again, it's a topic of a bit later talk, but DeepMind achieved good results with good old plain, almost plain RNNs, and later they created new architecture called Griffin. Griffin is a hybrid of these linear recurrent neural networks and local attention. And Griffin is a kind of production-like architecture. Google just published a model called recurrent Gemma. It's available in two sizes, 2 billion and 9 billion parameters. Not really large, like hundreds, but it's good. It's comparable to ordinary Gemma. If you know, it's ordinary Gemma is Google Open LLM, which is very competitive to, say, open source Llama. And what's important with Griffin and recurrent Gemma is it's fast. If you want low latency, if you want high throughput, it's much better than ordinary transformer architectures. Maybe it's hard to see here, but typical latencies are several times better than with transformers. So if you want on-device inference, if you want faster model, you can use recurrent Gemma. It's open, you can fine-tune it, you can train your own models on this architecture. So it's really competitive and interesting alternative. And later this year, another work came, XLSTM, extended LSTM. What's important, it was created by one of co-authors of original LSTM, Sepp Hochreiter, and that's a big deal. We can believe Sepp. He usually produces great work, and likely XLSTM has a bright future. I did not see yet any large models trained, but inside XLSTM they proposed two different sub-architectures, SLSTM and MLSTM, one with scalar memory, another with matrix memory, one of them easily parallelizable, another one not easily, but on their benchmarks it beats LSTM and other typical models, so it's an interesting alternative. Right now it's hard to predict which model will emerge with these new architectures, but we'll see. At least it's a very, very rich field. And last but not least, a big area called state space models, or SSMs. What are these models? These models use very specific representation. They implement this set of equations. And be careful, it's X here is not an input, X here is an internal state, and input here is U. But for those who come from control theory, maybe that's natural. For others who come from different field, that's maybe unnatural. Just keep it in mind. You can visualize this block this way. And what's good with, state space model maintain an internal state inside the model, like LSTM or like RNN. And later, a lot of development happened around this general framework. And typically all this development is done by specific group of authors that produce, I think, most of this model, maybe 90%, maybe even more. And usually every of their work contains of several parts. First, they announce and explain some new mathematical framework. So we use some new kind of matrices that generalize some previous approaches, and We implemented and achieved better quality, and we have a paper of 40 pages with a lot of mathematics, and that's it. After the original SSM paper, they propose Hippo framework. Hippo assumes a very special type of the A matrix. A matrix is this particular matrix that uses for transforming the internal state of the SSM. And if you use Hippo matrix of this type, you suddenly get significant boost in terms of quality on, okay, sequential MNIST is a very special data set, not related to production, but still it's a good benchmark, and huge improvement from 60% to 98%. It's a good improvement with just replacing, say, random matrix with another random matrix, but a bit more structured. Then they created another type of model called S4, structured space models. And the idea is you have a continuous state space model. Then you can discretize it and achieve something like a recurrent model. And with some other tricks, like, again, you use Hippo, you use some other special techniques, we will not dive here into it, you obtain a new model, more general than the previous one, and with better quality. And what's good for this type of model is that they have several alternative representations. First, you have recurrent representation, then you have convolutional representation. You can transform one into another, and you do not lose here anything. It's the exactly equivalent models. You just unroll your recurrent formula into a long convolution and use it, and it's highly parallelizable. All the NVIDIA GPUs are highly optimized for that. That's really cool. You can train such models very efficiently, and that's win-win. You have a model with recurrency. You can train it in a parallel fashion on large data sets. So looks like a recipe for good large LLMs, but strangely enough, in no of their papers they train a really large model. They train some models, several billion of parameters, and that's it. And every time you read a new paper, you try to understand what prevents them from making the next step and training, I don't know, GPT on new architecture. It's strange. Maybe it's just not enough time since the invention, but that's an open question in many cases. And all these SSMs have several representations. That's important. It gives you interesting ability to have highly parallelizable training and good representation with fixed state that allows constant inference time. That's really good. And now the challenge is not to get lost into all these abbreviations. You have S4, H3, and other models you face with, and in every paper they do a lot of comparisons with not a vanilla transformer, but with a lot of optimized transformer, like, I don't know, long former, lean former, big bird, performer. That's good models, which were originally much better than vanilla transformer, and this S4 was really good on, say, long-range arena. Long-range arena is a very complicated benchmark that assumes you have to solve tasks on very different long sequences, and on these long sequences, a typical problem is just to maintain context, and vanilla transformers just could not work with long contexts. Few years ago, context span for a typical transformer was, I don't know, 8K maximum, and that's it. And these tasks assume hundreds of thousands of tokens. So Mamba or S4, not Mamba, S4 works well with it. That's a good thing, but again, we do not see the really large model. H3, you can treat it as updated Mamba or updated S4. The idea was S4 worked well on some continuous domain tasks, but was not really good on language modeling. And in this paper, they proposed some adjustment to make steps towards language modeling and potentially to GPT-like models. And again, it was better by benchmarks. In parallel, a separate activity was to produce hybrids with convolutions. There is a separate lineage called hyena or hyena hierarchy and some other models from this family. It's very similar to one special convolution I mentioned before, when you have continuous convolution and unroll convolution into a very long kernel, and there is something like that in SSMs. And finally, there is a production-ready model called striped hyena. There were several models trained. One model for base pre-trained model for text, another model for chat, and another interesting biological foundational model. Maybe some of you who work in biomed may find it useful. Again, it used several architecture improvements, and what's important, it was competitive to open source good transformer implementations. For example, here you can see striped hyena. It's comparable to Mistral, it's comparable to Llama. Back then it was Llama 2. It's comparable to RWKV, so it's a pretty good model, at least it looks like. Again, latency is better than typical transformer model, memory footprint is better, so it looks like a good alternative. Finally, not finally, but later, Mamba came. You likely heard something about Mamba. Mamba, again, is updated previous architecture, S4. Right now, it's S6, because it's original S4 plus very special selection mechanism plus very efficient parallel scan implemented for computing this model. Again, a lot of tricks there. The block that looks similar to transformer block you see before. Again, no time to dive in. It's pretty complicated mathematics here. I just recommend to follow the links. I put a lot of links here. That topic deserves at least several hours just to get comfortable with all these new types of model. Just feel free to download the slides and follow these links. I also made a review of many of these papers in my Telegram channel. I added here links in case I made a review of this paper. Again, feel free to read it. It's Russian-based. Maybe it will help you. So Mamba is an interesting architecture, and later, actually in May this year, Mamba 2 came. Again, the similar approach. They proposed even more general framework that describes and incorporates new type of matrices. And in this particular work, they showed that transformers, linear transformers, and SSMs are the same class of models. Some conversions happening here. Transformers and SSMs are the same, and you can use all the tricks that were collected working on transformers in previous years here for SSMs. That's good, because for transformers, people spend enormous resources to find different things that work. We also knew that they found a lot of things that kind of work but do not change anything. And Alexei Gordich mentioned before that, okay, there are many transformer improvements, but in the end, they are not distinguishable from vanilla transformer. That's also the case. Still, Mamba 2 is here. Blocks of Mamba 1 and Mamba 2 looks complicated. And again, my goal is not to describe what's happening here. It's just for visual representation to understand that it's more or less same family, but with some differences. And in terms of comparison with transformer, NVIDIA recently did a great job of comparing Mamba 1 versus Mamba 2 and versus transformer, and they found that both Mambas are pretty good, and they beat transformer in some benchmarks, but they lose to transformer on other benchmarks. And NVIDIA proposed a good solution. Let's create a hybrid. Let's take Mamba 2, let's add some transformer blocks there, and finally hybrid beats anything. That's a good old trick. There are, I think, several tricks in ML. First, do ensembling. It helps almost any time if you can afford it. Second, do hybrids. You can treat it as ensembling as well in some sense, but architectural ensembling, that works. And right now we have some proven hybrids. Again, it still was not a large model, just 8 billion of parameters, but again, it's comparable to small open LLMs that already very, very practical. And the most interesting part is right now there are some production-ready open models. First of all is Jumbo. Jumbo was created by AI29. It's, I think, Israeli company. And they created a hybrid, SSM and transformer. They used Mamba blocks, they use Mamba mixture of experts blocks, and they use transformer blocks. And this architecture is a highly hybrid architecture. You have a single Jumbo block consisting of 8 other blocks. Among these 8 blocks, 1 block is transformer, 3 blocks is Mamba, and 4 blocks is Mamba mixture of expert layer. I think you cannot invent such architectures if you don't have a large cluster to just experiment with all these combinations. Likely they did something like that. They trained a model with 12 billion active parameters because of mixture of experts. The original model is larger, it's 52 billion. And it has pretty big context window. Not many transformers can be compared here, and it has a very good memory footprint. You can fit 140,000 K context on a single A100 GPU. That's good. Other models like say Llama, far from it. So it's a really competitive model. It's good. And in terms of quality, again, it's Jumbo. Looks good. It beats Gemma, it beats Mixtral, it beats Llama 2. Again, right now you have newer Llama, newer Gemma, but for the beginning of this year, that was good result. And surprisingly, just 2 weeks ago, a new Jumbo was published, Jumbo 1.5. And what's important with this Jumbo, there are 2 versions. One mini version is almost the same as original Jumbo, not really interesting. What's interesting is Jumbo Large. Jumbo Large is a really big model. It's almost 400 billion parameters. It's a mixture of experts, active close to 100 billion parameters. It's multilingual. What's important, it has advanced capabilities like structured output, like function calling. So it looks like a really good production-ready LLM. And in terms of independent evaluations, you probably know artificial analysis quality site. You can compare different LLMs there, commercial and non-commercial. And in terms of quality on very different benchmarks, Jumbo is pretty good. It's better than Gemini 1.5 Flash. It's better than Claude 3 Haiku. It's not far from GPT-4o Mini. Again, it's not the top level, but it's pretty good level. You can take this model. It's kind of open. The license changed since original Jumbo. Original Jumbo was Apache 2.0. This Jumbo is Jumbo Open Model License. It limits commercial applicability of this model, but at least for research you can use it, and it looks good. It's really competitive. And what's interesting, they compared this model on long context tasks, and they claim that regarding effective context window size, so what context you can work and you do not lose any quality on long context, they claim that both Jumbos works well on really large context, larger than 200K. And all the other models, like say Gemini 1.5 Pro, which kind of have context of 2 million tokens, it's not so good on benchmarks like this. They used a ruler benchmark, so they have large context, but you miss some facts on this context. Your quality of your results are suboptimal. So Jumbo is a really interesting thing, so worth trying. Again, it's better in latency, it's better in throughput, so looks good. Another interesting Mamba model is Codestral by Mistral. They published open model for code. You can use it with a very permissive license. It's not a really big model, just 7B, but still it's good. So you see there are some alternatives right now. There are open alternatives. Some of them are competitive, so it's interesting time. Hydra, bidirectional Mamba, again, the same step, even more general framework, even more general matrix representation. They fit many different models into a single framework. Right now we have a framework that incorporates MLPs, MLP mixer, transformer, linear transformer, S4H3, Mamba, Hydra. All these models, on some sense, mathematically can be described by a single framework. I think that's an important result on its own, so that's interesting. But I want to finish on the important thing. There is a drawback with all these SSMs. SSMs have a perception in the industry and the field that it's kind of a replacement for RNNs. What's good with RNNs? RNNs are Turing complete. You can potentially train, learn anything that is computable, almost any algorithm, anything. That's a good ability. In practice, it's really hard to train RNN to solve many algorithmic tasks, but still, there are some specific tasks that RNNs, even simple RNNs, can solve, but transformers, linear transformers, and SSM cannot. So essentially, SSMs and transformers lies in complexity class that is simpler and more easy than another complexity class where RNN is. So keep this in mind and do not equate recurrent neural models to SSMs. It's still different thing in terms of complexity, in terms of which tasks they can solve. There is the problem here. And I highly recommend this video by authors of this article just to understand what they did, what specific model tasks they tried, and where RNN are still better than SSMs or transformers. So that's it. What's the conclusion? First of all, for transformer, there are right now many viable alternatives, and right now there are some open models, usually small models, that are really competitive. If you want to solve some specific task, right now you have some options, and if you need some specific features like low latency, high bandwidth, you can use these models. That's good, especially if you need to do something on device or in limited resource setting. That's a real viable alternative. The problem is right now there are no really big models that are competitive to LLMs except Jumbo 1.5 large. That's the only known exception. If you know anything else, let me know. Maybe some companies internally have some alternative, but I don't know about it. But my expectation is that this year and next year we'll see much more interesting models, likely hybrids, that will be competitive to transformer even better, and that can potentially be trained faster with longer contexts, and we'll see. My bet is we'll see something like GPT, but on this new architecture that will be faster and with very, very long context. I'm waiting for it. So that's it. Thank you. Please use these slides to follow the links because otherwise it's really hard to get into this field. All this SSM stuff, it's really complicated, and it's really worth spending, I don't know, hours or maybe days to just read carefully all these papers, try different learning materials, view some videos. There are good amount of quality materials there. So my goal is just to highlight that there is life outside transformers, and just look there and try. So thank you. If you have any questions, please feel free to ask me.
I wonder, did you study how these models handle synthetic data, whether they are robust, have you compared them with synthetic data?
What's so special in synthetic data?
Because it's actually generated, and sometimes, it has probably less entropy than the common data.
I think in some papers there were some synthetic data sets. I'm not sure. It has to dive deeper and look carefully. I do not remember any specific problems with it mentioned, so not sure. And I personally do not expect any big problems here. Maybe the same problems you'll have with synthetic data or with transformers and any other architecture. Any other questions? Oh.
Hello. Hello, thanks for the talk. I wanted to ask, in a lot of the state space models and like other variations, transformer essentially becomes a special case of those models. And I wanted to get your 2 dimes on the opinion of, are we thinking about this architecture creation correctly in terms of how should it be done logically, not just by solving engineering problems, and coming back to the whole same idea of, everything that's good with transformer, we can have it as a SAM. Do you see any type of like more symbolic paradigms coming into state space models and other alternatives to transformers in the vicinity of the future?
Oh, that's a good question. It's hard to predict. Symbolic. There are a lot of movement right now to create hybrids, like neuro-symbolic integration and something like that. I do not expect right now that these models, the models of today at least, will change this field significantly, because they're in the same class of like transformer, and I do not see any good examples of using any specific things that improve, I don't know, reasoning abilities or symbol-like processing, but we'll see. Likely some group right now will develop some advanced models which is better for symbolic processing. Say, we'll see. It's really hard to predict.
I have a question around, you alluded on that people started to write how transformers are a type of, that there is a kind of like unifying framework of writing this. Like one of my colleagues, I think, said they're all message passing neural networks with different adjacency matrices. And he said it in the structured state space that there are these restrictions on the matrix A to be like low rank, etc. And I think if I remember correctly, they also did a lot of work in actually optimizing the GPU memory, which is a little bit in the paper. So what are your thoughts on to what degree are we kind of like digging ourselves into more of a hardware minimum, where we're trying, and the reason why all of these are transformers are somewhat the same state space models, because the usage of like matrices are like using GPUs and chips that are optimized for matrix multiplications. So the hardware is getting optimized for these methods, and the methods are being optimized for this parallel compute. Do you see an alternative universe where we will have a different hardware that will maybe be better for graphs, or that could unlock a different kind of paradigm to get us out of this?
Yeah, with hardware there are already different universes. You have graph core, you have Cerebras, you have I don't know, even memoristic architectures. Okay, it's a bit too early for production, but still, we actually is in a strange situation. Transformers won the hardware lottery, and a lot of people created a highly optimized code for transformers, and right now a lot of movement to apply the same highly optimized code for transformers to new models, and with these, how to say it, with these general frameworks that gather different SSMs and transformers under a single umbrella, it's easier to use these things. But with completely different models, like I don't know, graph models, definitely other types of architecture could be better, and I believe will be better.
Do you have a guesstimate? What would be your bet? Like, you mentioned Cerebras and graph core.
Yeah, I like Cerebras. It's a very interesting approach, and graph core is also interesting. But this field is again highly dynamic. I suppose there are some new hardware vendors that I don't know, and that I don't say create very special architecture for graph models. Again, hard to predict. It's very capital-intensive field, and for many companies, it's really hard to produce some new hardware. And as we know, with in NVIDIA case, that's not enough. And that's especially highlighted on AMD. AMD produce great hardware, but they lack CUDA. You don't have all this software infrastructure, and that's it. No one research can use it, and even with great hardware, you can't do anything. So that's a problem. You need to build the whole stack, and that takes a lot of money, a lot of efforts, and we'll see who can compete.
Okay, so with so many different types of models, is there any research on what relations are there between different models, so that one of them, for example, can be converted to another? Say that one model has one advantage. For example, it is easier to train in parallel mode, while the other one is cheaper to execute. So that you train one model, then convert its weights to the other model.
That's an interesting question. In some sense, you don't need to do it with SSMs because they just have different representation, and you use a representation that suits your current needs, and that's it. You train it parallel, then you inference it in a recurrent mode, and you don't need anything. But there are some works when people try to convert one type of model into another. It's really hard. I think the more viable thing is distillation. You train one large model of one architecture, you can distill it into another model, maybe smaller and a different architecture sometimes. And what's interesting, in some cases you even get higher quality than the original model, and some tricks like self-distillation work here. That's a separate area, but it's interesting area. Overall, I believe there are limits of what you can convert, because we know that different models are from different computational classes, and you just can't convert in some cases, but it's an interesting approach. No major achievement right now that you can use and get and use in production. So.
Hello, thank you for the talk. So I was wondering whether there are any research or that you are aware of happening in vision field, so SSMs for vision tasks, similar to vision transformer or something like that.
I didn't hear good examples on vision. Maybe it's just to come.
There's Mamba Vision.
Mamba Vision, yeah?
From NVIDIA.
Oh, Mamba Vision from NVIDIA. So.
I have a bit of a philosophical question outside of all this. Do you believe there is that, like, in the search for like ultimate architecture, going through directions of some engineering hacks from some sequential hack, do you believe there is this type of a God architecture? Let's call it quote unquote like ultimate architecture that can solve like all types of problems simultaneously, will be parallel, will run great on CUDA, like all of these good qualities. Are we, essentially what I'm asking, are we converging towards something that's ultimately good and shall be perseverant, or are we still very far off?
Can I rephrase it? Can we solve free lunch theorem?
Yeah, essentially it boils down to this.
Yeah, I think no way to do it, and I don't expect there will be one overall architecture. Maybe Turing machine that is that kind of architecture, but it's not efficient for many tasks, and you need special architectures to do it in parallel and other. So mathematically maybe, but practically I don't believe it.
Fair enough. Thanks.
So it seems that's it. Thank you. It was pretty information-intensive talk. I hope I gave you enough links to follow, and please explore these new types of models. They are really interesting, and keep an eye on this dynamic field. Everything changes so quickly. I believe until the end of the year we'll see some new models, at least one or two by the authors of Mamba, and some production models, maybe hybrids like LLM replacements for, I don't know, Gemma, Llama, and other models. Keep an eye on it. Thank you.